Suppose we have any triangle at all, not necessarily a right angled triangle. Let's call its sides A, B and C. And let's call its angles also A, B and C, but using capital letters to distinguish them from the sides. In each case, the angle is opposite the side with the same name, so angle big A opposite side small a, etc. Although our triangles can be given to us in any position at all, it'll be easier for us to see this if one of the lines is horizontal, so let's just rotate this around. We'll drop down a perpendicular line from the top of this triangle to its base. This will divide it into two smaller triangles. Because the line we've drawn is perpendicular to the base, both of these new triangles will be right-angled triangles. We'll let the length of the perpendicular line we've dropped down be called h for height, and we'll call the length of the base of the triangle on the left w. This will mean that the length of the base of the triangle on the right is c minus w, and just for clarity we'll remove the label c. Now we can do some calculations. Because the triangle on the left is right-angled, we can use Pythagoras' theorem to deduce that w squared plus h squared is b squared. Similarly, the triangle on the right is right-angled, so again using Pythagoras' theorem, we have that c subtract w squared plus h squared is a squared. Let's just rearrange both of these to make them h squared is equal to. So in the first case it's b squared subtract w squared. In the second case h squared will be equal to a squared subtract c minus w squared. So we have two different expressions for h squared which we can set equal to each other. So we have that b squared subtract w squared is the same thing as a squared subtract c minus w squared. Let's expand that bracket on the right hand side. So we have that b squared subtract w squared is a squared subtract c squared subtract 2c w plus w squared. Therefore b squared subtract w squared is a squared subtract c squared plus 2cw subtract w squared. Realizing that both of these sides end with a subtract w squared, we can add that to both sides to end up with b squared is a squared subtract c squared plus 2cw. And then just slightly rearranging this, we have that a squared is b squared plus c squared subtract 2cw. But looking again at the right-angled triangle on the left, that triangle has a hypotenuse of b, and the side adjacent to the angle A is w. So using the definition of cosine, we have that the cosine of the angle A is equal to w divided by b. Rearranging that, we have that w is b times the cosine of A. If we substitute this into the expression we've just derived, we have that a squared is equal to b squared plus c squared subtract 2. Instead of w, I can write b cos A. I'll write the b first, then the c from the expression we already had, and finally cos A. This result is called the cosine rule. Formally then, the cosine rule says that in a triangle such as the one we've just been looking at, a squared is b squared plus c squared, subtract 2 times b times c times the cosine of A. You can think of the cosine rule as a superversion of Pythagoras' theorem. If we had a right-angled triangle with the hypotenuse of A, then a squared would be b squared plus c squared. What the cosine rule tells you is how to adjust this if the angle opposite the side that we just called the hypotenuse is not a right angle after all. You have to subtract 2 times b times c times the cosine of that angle. There was nothing particularly special about the angle A that we used in that derivation. So we could have done it by dropping a perpendicular to either of the other two sides, which would have given us these alternative forms of the cosine rule. At this point, it may be starting to look a little more complicated than we'd like it to. However, a picture will help keep all this a bit clearer. Rather than worrying about exactly which sides or angles we're going to call A, B, and C, think of it like this. The cosine rule connects something about one side of a triangle on one side of the equation, and the other sides of the triangle and the angle between those other sides on the other side of the equation. So, rather than thinking about a squared being b squared plus c squared minus 2bc cos a, I would think of it like this. In the picture we've got, the length of the red side, squared, is equal to the length of both of the other sides squared and added together. Subtract 2 times the length of those two other sides multiplied together, times the cosine of the angle in between those other two sides. So on one side of the equation, the red line, on the other side of the equation, everything to do with the blue lines and the angle in between them. Let's see some examples of what we can do with the cosine rule. Find the length of the side labelled x in the triangle below. This question is asked in just the right form to use the cosine rule in the way that we have described. The length of the side called x squared will be equal to one of the other sides, let's do the 7.9 length squared, plus the length of the other side, 8.2 squared. Then we have to subtract 2 times one of those other lengths times the other length, and then multiply by the cosine of the angle in between them. So using a calculator, we can immediately work out the value of x squared. That comes to 178.18 to 5 significant figures. I'm using 5 significant figures because the final answers should usually be given to 3 significant figures, and this will avoid rounding errors. Of course, I've just done all of that in a calculator, which is perfectly acceptable. This gives us a final value of x of 13.3 to 3 significant figures. Looking back at our diagram, that answer seems completely reasonable. It's always nice to have a little check to see if the answer you've got does fit in with the picture that you've got. In this question, we're again being asked to find the length of the side labelled x in the triangle below. This is similar to the last question, but this time the side that we don't know is not in the most ideal position that it could be. But let's just start going ahead with the cosine rule as usual. So, we have that the side of length 4.8 squared, that will be equal to the side of length x squared, plus the side of length 5.5 squared. Then we have to subtract 2 times x times 5.5 times the cosine of 51 degrees. As before, one side of the equation has a side which in this case is on the top. The other side of the equation has everything to do with the other two sides and the angle between them. So using a calculator to evaluate some of the pieces here, we have that 4.8 squared is 23.04. That's equal to x squared plus 5.5 squared, which is 30.25. And then we will be subtracting 6.923x, where that number has been calculated to 4 significant figures. Now, at this stage, things aren't looking so great, but if we glance again at that equation, we realise that it's just a quadratic equation in x, and we have lots of experience of dealing with those. So, let's rewrite everything on one side. We will have the x squared, subtract 6.923x, plus 7.21 is equal to 0. And now we can solve this using our favourite method of solving quadratic equations. Because the numbers are so appalling in this case, it probably is best to use the quadratic formula. So we will have that x is negative b, which is 6.923, plus or minus b squared, which is negative 6.923 squared. Subtract 4 times a, which is 1, times c, which is 7.21. All of that needs to be rooted and then divided by 2a, divided by 2 times 1. That gives us two possible values of x. Either x is 1.28 or x is 5.65, both given to three significant figures. So which is it? We're going to have to go back and look at the situation that we've got. Looking at this picture, it's quite clear that the shorter length is just far too short to fit in with all the information we have got. So, therefore, it must be the case that x is 5.65 to three significant figures. We can also use the cosine rule to answer questions about missing angles, so long as we know all of the sides of the triangle. In this case, we can write the cosine rule in the form 12.4 squared is equal to 23.3 squared plus 14.2 squared, subtract 2 times 23.3 times 14.2 times the cosine of the angle between those last two sides, which is the x that we don't know. We can then rearrange this equation. Let's do it slowly. First of all, let's move the 2 times 23.3 times 14.2 times the cosine of x to the other side of the equation. That leaves us with the 23.3 squared plus 14.2 squared. We have to subtract the 12.4 squared from both sides. Now, if we divide through by the 2 times 23.3 times 14.2, we have that the cosine of x is equal to 23.3 squared plus 14.2 squared, subtract 12.4 squared, all divided by 2 times 23.3 times 14.2. You could of course evaluate a lot of these things earlier on. I quite like to leave it a bit later than that. Here I can still see where all of the numbers have come from. If I had simplified too much, it'd be difficult to know quite where I got those numbers from, and if there was a mistake it would be quite hard to track it down. But having got this far, we can now deduce that the cosine of x is 0.9055 to four significant figures. Always use more significant figures than is required in your final answer. And that gives us a value for x of 25.1 degrees. Returning to the original picture, that's not an outrageous answer. That angle is fairly small.